Hello learners, welcome to session 4 of unit 3, the division algorithm. In this session, we will give properties of divisibility of integers, which you can prove very easily. I'm your course instructor and my name is Michaela Desmani. By the end of this session, you should be able to define the division algorithm. Should be able to explain the terms, quotients, and divisors. Identify the greatest common divisor (GCD) of integers. You should be able to also identify numbers whose GCD is 1. Whose GCD is 1. Definition. Let A and B be members of Z, where A is not equal to 0. Then we say that A divides B if there exists an integer C such that B equals to AC. We write this as A divides B, as this A divides B. So A divides B, we write this as this, and say that A is a divisor or a factor of B, or B is divisible by A, or B is a multiple of A. All these are the same. If A does not divide B, we write it as this. Here, some place write it like this: A, then there's a space between the division and then B. Or some people also write it like this: A does not divide B. So any of them, but in this course, we may stick to this. A does not divide B, and that's how we write it. Okay, so let's look at this theorem. If x and y are members of Z, which is well mean y not equal to 0, then we can write this: x equals ky plus r. Actually, y is positive. Y is positive for the given interval. So when I have 7 divided by 2, and the result is 3, remainder 1, then I can write 7 is now equals to 2 times 3 plus 1. Okay, something like that. So here in the above, the integer q is called the quotient of x and y, quotient of x and y on dividing x by y, and the integer r is called the remainder x and y on dividing x by y. Okay, so this proof here, you can also prove this. So simple to see the beautiful of mathematics. So learn how to prove. Now let's find out, let's look at this corollary. For any two integers x and y with y greater than 0, there exists unique integers q and r such that x equals to ky plus r, where this is the given interval. So this is pretty simple. From the recent theorem, there exists unique integers q and r such that x equals to this, where y is actually positive. So since y is positive, that's y greater than 0, implies that x is actually equals to ky plus r for this interval. So simple. So we can see the beauty of mathematics. And here are very. So find out the clear difference between corollary, lemma, and theorem. Find the clear distinction between these three if you don't know them. Also, you can also find them in the nature of mathematics. Divisors. Let's see, what do you mean by divisors? So let's x, y be a member of Z as usual. X not equal to 0, then x is said to divide y, or x is a divisor or factor of y, and write it as x divide y. Provided there exists q be a member of Z such that y equals to qx. In that instant, we say that x divides y. X divides y. Example is when I have, let's see, let me use 8 divided by 2. What do I get? I get 4 times 2. Exactly. So it will go into it exactly. So, and then, so this 4 equals to 4, not 4 times 2 equals to 4. But somebody can write 8 equals to 4 times 2. Great. So let's see the next one. Okay, let me clean this. Okay, the next one says that let x, y, z be integers with x not equal to 0. Suppose x divide y, and x divides z. Then for all integers x and t, x divide s plus y, and then also divide t plus z, and that is clear. That is clear. It divides the sum. Okay. Also, let xy be a member of z, and non-zero integer c is called a common divisor of x and y. If c divides x and c divide y, then we say that c is a common divisor. It divides all the two. So when I have 4 and 8, and I take 2, it's one of the common divisors. I take the same 4, it's one of the common divisors. It divides all the two integers respectively. And a zero integer d is called a greatest common divisor, GCD, of the integers x and y. If firstly d divides x and d divides y, then once it divides all the two, we say that it's a common divisor. For all c be a member of z, if c divides x and c divides y, then c divides d, then c divides d. Once this condition is satisfied, then we say that it's a greatest common divisor. The greatest common divisor. Okay, that is very, very interesting. So let's look at greatest common divisor. Let d and d prime be two greatest common divisors of integers x and y. So we have d and s prime are the two common divisors of x and y. So d divides d prime, and then d prime also divides d. Okay. Hence, there is this integers u and v such that d prime equals du. Because once d divide d prime, you can say that d prime equals to du. And other one too, you can also say that d equals to d prime v. Okay, it's d prime v. Okay, so therefore you can see that d equals to u v. Why do we say d equals to du v? D equals to du v because d equals to d prime is du. So when I put the d prime here, I put this d prime here, and I get du v. That's a du v over here. Okay, which implies that u v equals to 1 since d is not equal to 0. You factor out d out, or you divide through by d, and d is not equal to 0. Once I divide through by d, I get u v equals to 1, and that is this condition. That's either u equals to v or equals to 1, because we are saying u v equals to 1. So either u equals v or equals to 1, or u equals v or equals -1. If both are -1, we get -1. If both are 1, we get 1. So if both are -1, we still get 1, and if both are 1, we still get 1. Hence d prime is either plus or minus d. It now follows that two different GCDs of x and y differ in their sign. Of the two GCDs of x and y, the positive one is denoted by this GCD of x and y. That's the positive one in the course of this section, and then this course we'll be denoting the positive GCD as GCD then xy. So when you have 2 and -2 being the greatest common divisors of 4 and 6, we are interested in the positive one, so we say GCD of 4 and 6 equals 2, or 2 equals to the GCD of positive 4 and 6. So that's what we are going to denote in this course. Let's look at theorem. Any two non-zero integers a and b have a GCD, and GCD of the two is given by ma plus nb for some m and n being integers. Okay, so to shorten this video, I give this one to you as an assignment. So this is an assignment, go through similar like the one we just discussed. You prove this one and you see the beauty of mathematics. So simple. Example 16. Let A and B be integers such that GCD of A4 equals to 2 and GCD of B4 equals to 2. Now I want to prove that GCD of A plus B4 equals 4. Okay, so the proof is here. I think you understand this and I don't need to go through, but let me explain some more. Since GCD of A4 equals to 2, here implies that 2 divides 4. Once 2 divides 4, automatically 4 does not divide A. Therefore, if 2 divides A, then A equals to 2x for some integer x such that the GCD of 2 and x equals to 1. Similarly, B equals 2y, and the reason is that 2 divides B for some integer y such that GCD of 2y equals to 1. Thus, x and y are both odd integers, and that is true. So this implies that x plus y is even. Once you add two even number odd integers, you get even. So x plus y actually equals 2n, which is even for some integer n. Now let's see, by adding a plus b, b is 2y, a is 2x, so we get x 2y and then 2x, you factor 2 out, you get 2x plus y, and that will be equal to 2 times 2n, which is 4n. And then GCD of a plus b and 4 is actually the GCD of 4n and 4, which is equals to 4, and that is a proof. So simple. So you see the beauty of mathematics in that instance. Abstract algebra. Great. Example 17. Find integers x and y such that 5, 1, 2, x plus 320y equals 64. Okay, I leave this integer. I will do this solution in section 6. That will be the last example in section 6. So by section 6, all that I want to use, all the theorem and then the ideas I want to use, I've captured everything. So I will leave this one and I'll do this in section 6. Relatively prime numbers. If GCD of a, b is 1, then the two integers a and b are said to be relatively prime or co-prime to each other. Once their GCD is 1, they are relatively prime to each other. Using the theorem on GCD, we can say that a and b are co-prime to each other if and only if there exists M, A being a member of Z such that 1 will be equals to MA plus NB, and this is true, and I think we've done that. The next theorem shows us nicely property of relative prime integers. Let's see the properties. If A, B, C are members of Z such that the GCD of A, B equals to 1 and B divides AC, then we can say that B divides C. So let's prove this. We know that there exists M and N being a member of Z such that 1 will be equals to this, and this one from equation star we made mention. If that's true, you can see that C is actually the same as C times 1, and that is true. If you agree to that, then you make 1 the subject. 1 is MA plus NB. Putting 1 here, that is MA plus NB here, we get this. So multiplying this or expanding the brackets, we get this one. Now, you can see that B divides AC and B divides BC, and that is true. Therefore, B divides the sum, that is MAC plus NBC, and that is true. So simple, very interesting.